So we're going to get started with the next section. So we're going to be starting to talk about the LED calculator design. You guys just learned a little bit about binary and logic gates, so now we're going to apply that to our calculators. So we're just going to do a little bit of review. So I didn't fill out the first two, but so these are the main gates that we're going to be using. So the NOT gate, which basically just inverts what it's given, and where both inputs need to be a 1 in order for the output to be a 1, or where at least one input needs to be a 1, and XOR, which only one input can be a 1 for the output to be a 1. So those are the main gates we're going to be using for this project. So Boolean Algebra is the way we use to describe these. So instead of writing the words and or not, and keep on having to write those, we use symbols to represent these. So for not, we'll either use like a tilde or we'll put a line on top of the variable that we want to not. For and, we'll use multiplication, so either a dot or an X, whatever you like to use for that. For or, we will usually use addition, so the sum symbol. And then for exclusive or, we'll be using a circled plus sign, so direct sum. So yeah, and those are the symbols we use. And so if you guys follow, it's going to be on chapter 15. It's one of the first tables in that chapter. There's going to be this chart, approximately. 14. 14, yes.
Is that it?
Yes, yes.
Page 139.
So it's going to be on page 139. So have you guys filled out these charts already? Yeah, so yeah, if you guys could start filling these out. So fill this one out. Yeah. So get used to the terminology. So. Yeah, zeros and ones. Right, so the first two columns are going to be the nots of the, so A and B are basically your inputs, and these are the values we're going to be giving you for those rows. First two columns are the nots. Second two columns are ands. Next two are ors, and the last two are exclusive ors. So that helps.
See if this one works. I don't know what's left in.
How many people are already done with their charts? Okay. We'll give like 5, maybe like 3 or 4 more minutes.
Now this one is a little different because maybe this was the north. So look over here at this tape. So
We're just gonna start going over it. If you haven't finished, we'll go over all of the answers, so don't worry. So we're gonna go row by row and go through the answers. So for the first row, what's not A?
1.
1. Not B?
1.
1. A and B?
0.
0. B and A? Does anyone have that?
I have it, but I'm just giving
Yeah,
you
so B and A is also 0. A or B, it's going to be 0.
all of those are zeros.
Yeah. B or A is 0. And then A XOR B is 0. And B XOR A is also 0. So then let's go to the next row. So
And it might be easier for people to understand if you do them by the columns going down versus the rows across. So there
Down.
needs to be any patterns that may or may not occur. Or from, we did these earlier with the switches with that program.
we'll just go for rows by now and then maybe the next ones. So for A0, B1, not A, 1, not B, 0. A and B, 0. B and A,
0.
A or B,
All
1.
of them are ones across after that.
B or A, 1. A XOR B, 1. B XOR A, 1. Okay. The next one, not A is 0. Not B is 1.
1.
AB,
0.
0. B and A,
0.
0. A or B, 1.
All the rest are ones.
Then B or A, 1. A XOR B, 1. B XOR A, 1. So, and then last one. So not A, 0. Not B, 0. A and B, 1. B and A, 1. A or B, 1. B or A, 1. And then last two XOR A XOR B, 0. B XOR A, 0. Yeah, so.
I'm sorry, what were the last two?
Oh.
Oh, the answer.
0 and 0.
All right.
Yeah. So did anyone notice like any patterns with these that we gave you? So did it make like a difference if we had A, like if we switch A as the first variable we listed versus B? No. Okay. So the reason we call it Boolean algebra is because it has many of the same properties as the arithmetic algebra. So this is our commutative law. So basically, it's just stating that the order that we state things doesn't matter. It's more about the actual action. So A and B is going to always be the same as B and 1, B and A. A or B is going to be B or A, and then vice versa, so on for all the other functions. Yep. And so then we have another table. It's going to be the next one. We have another table. So I'll give you guys like a few minutes to fill this one out as well. And if you're done with that one, there's more if you want to fill those out as well. Is there any way we could just project this onto the whiteboard itself? Just project onto the whiteboard so I can like write on the.
Well, yeah, you just pull the screen up. Just raise the screen.
without turning off the projector.
Yeah.
Yeah,
Yeah,
there's which button is that?
What did you say?
Is it possible to just raise the screen and not turn that off? Okay. So is there anyone that wants to, while everyone else is still working, does anyone want to fill out the first 2 columns maybe on the board?
I hope they're right, but I don't know. Because I have questions on one of these. These are the ones I have questions on real quick. Maybe you could tell us about this one. So like when you get these, you know how you're supposed to get a 2, but a 2 is not a 2? So do we write a 1? What do we?
I mean, so right now we're just doing comparisons. So these are just comparisons, right? So.
Oh, we're not writing them in binary?
We're doing binary, but we're not, see, when we're not doing addition, so, right? Because the plus sign is actually an OR, so it's an OR. So we're just checking that at least one of the inputs is 1, and if it is, then the output is 1.
Gotta go back. Gotta go back to the board.
Yeah.
So there's 3 toggles, but when it says A or B in the first column,
Yeah.
so I see like 2 toggles is connected to or, but what about the third one? Like if it's just telling you A or B, like what is this connected to?
So for the first column, the C won't matter, but it's more for the other ones.
So C is not connected to
Yeah. So, but then for the second column, you're gonna compare. You're gonna do the result of this ORed with C. So that's why we have this column first. So it's just this.
We're doing A or B, we're not even thinking about C.
No, because he's not even an expression. But that's just there so you can do this one and then directly compare these 2.
I'll give it a try. I'll give it a try. Let's just see what happens. They may be wrong, but I'll just put them just to move this along. Thank you. All these were 1s. Is that right?
Yeah.
Is that what you all have? Is that what you all have? And then this one, I didn't do the last one, but, okay, 0, 0.
Right, so then the second column you're ORing with C.
Yeah. I had put this, but again, this may be wrong because I need to go back and look at the logic behind it. So I don't know.
Does anyone want to do the next 2 columns?
Are they right? That's the question. Terry, did you do the?
I'll try.
So this one you can find out.
Which one is this?
Does anyone want to do the next column? Is everyone ready? We can just go over the rest of the answers, so that's fine. So we had 2 of you come up and do them, and yes, they're all right. So yeah.
I'm just trying to put some logic in here.
Yeah.
Sometimes he said I have to accept
Yeah. So for
behaviors as they are.
So for A or B and B or C, that's just like an intermediate row. So as long as one of these 2 variables was 1, then the result was 1. And then we use those to compare the next 2 rows to either. So for this case, this result compared to C. And then in the other row, we're comparing B, the result of B or C to A in OR functions. And then with the last 4 rows, instead of doing ORs, we're doing ANDs. So as long as both inputs were 1s, then that function was also a 1.
Okay.
And then we ANDed that. The output of that, we ANDed with either C or A and the other one. So I'm going to put the answers on the board and then erase these. So if you guys want to just check over that you guys got these. Does everyone understand the logic so far? We're good on how this is working? So did anyone notice like any patterns with these, like with any of these? Yeah. So the associative probably so, right? So so our 5th column and our 7th column have the same answers as well as our last column and our 3rd to last column. So this is our associative property.
Can you go back one more time?
Oh,
So
sorry.
I know they're in the back of the
There you
book, but I don't want to look it back.
You're good.
Those are the answers we put to the last one. Thank you. I don't know if anybody else.
Is everyone else good? Alright. So yeah, this was the associative property. Sorry, it's kind of hard to see. So basically saying that for when we're comparing 3 of these things, it doesn't matter which 2 we compare first, what order we put these in. If they're all going through the same kind of function, the result will always be the same, right? So if we're doing AND, it's a little hard to see. As long all 3 of them need to be 1 in order for the result to be 1. It doesn't matter which order we analyze, like looking BC first and then looking at that compared to A or vice versa, whatever. As long they all need to be 1. For OR, right, it doesn't matter which order we compare them. As long as one of them is 1, then the answer will always be 1, right? Because the condition for OR is that at least one has a 1. And then for XOR, the same property kind of applies. Only one of the variables can be a 1 in order for the total answer to be a 1. So last table. So it's going to be the next one. So I'll give you guys a few more minutes to fill this one out if you haven't already. Does anyone want to come up and fill in some of the columns while everyone else is still working on some of the others, maybe? Fill as many as you would like. Does anyone else want to do the other ones? Or oh. You can fill out however many you feel comfortable.
So this is A and B or C, right?
Yeah, so you're gonna do basically A and whatever the result of this is. It's gonna be the same as the first two.
Oh, yeah.
Yeah.
Should we just finish?
Yeah. Do you want to fill the other ones out, or?
It's just for you to do your eyes to read across this.
This is different.
Oh,
Yeah.
right. The book is a typo.
Yeah, I can do it.
Yeah, if you could do it. Yeah, the book's kind of typoed. That's supposed to be the
Okay, he'll fix it.
this is
141.
141. Yeah, it's supposed to be B exclusive C, so you can plug that into this equation here.
I don't know, I think it's right.
Yeah, you're right. You're right.
Right
You're right.
there. The AB exclusive AC. AB exclusive AC, is that 1 or 0? The last,
The last.
you go down. Again, AB exclusive AC. Not A parentheses, exclusive BC, but,
Oh, this one.
yeah, go all the way down. That one.
Yes.
What should that be?
Right. So we already solved A, B, and AC. So those are the values. So 1 exclusive or 1, right? You can't have both of them be 1, so that's going to be a 0. Yeah. We just have these other columns here just to be. These are the plug-in values. So yeah.
Following along.
Right. So I'm gonna erase these so I can put up the printed ones. So those are all the correct answers. So does anyone know what the law that was used here is called, or property, whatever you like to call? So I'll just give a few minutes for people to check that their answers are right or not. So,
Oh, I see, okay. Sorry, so we have.
so this is, oh, do we still need the other table? Yeah, we're good. So, yeah, so this is our distributive property. So when we combine our AND statements and our OR statements and our XOR statements, it behaves kind of like how we do math when we're doing multiplication and stuff in parentheses. So it's basically saying how if we have something in parentheses and we are trying to AND that, we can kind of multiply that thing out into two parts. So for one of them, it's for the A parentheses B plus sign C, so would also be equal to A and B or A and C. You guys kind of saw this in the tables you filled out, and then same thing for XOR. And so the reason why we call this Boolean algebra, even though we're not really adding anything, it's just more of a comparison, we just do this because we find that we can use a lot of the same properties in algebra to do some of our equations to compare a lot of these variables. Is there any questions so far? Okay. I'm going to pull the screen down now because I don't think we need. So now we're gonna move on to our calculator. So now we're not thinking about Boolean algebra. We're trying to add numbers now, right? So normally when we're adding numbers, we use regular numbers. So that go from like 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's gonna be in base 10. We have 10 digits from 0 to 9, and then each digit or placeholder is gonna be a factor of 10. So right. We have our ones place, our tens place, our hundreds place. Those are all factors of 10. Meanwhile, in binary, we have base 2, so we only have zeros and ones. But then each place is going to be representative of a factor of 2. So our first digit is still going to be 1 because that's going to be 2 to the 0. But every place afterwards is going to be representative of a factor of 2. So we're going to go from 2, 4, 8, 16, 32, so on and so forth. We can use binary to represent any number as well, with powers of 2. So when we're trying to add things, right, when we do decimal, we can just do, if we're trying to add 1 plus 1, we can just say 1 plus 1 is 2. We know that, right? But in binary, we don't have 2, right? So when we're doing 1 plus 1, it's technically 2, right? But we don't have that digit. So it's going to be kind of like when we do 9 plus 1, right? Our answer is going to have that digit is going to be a 0, and then we have a carry. We carry that 1 over here to the next place, which is going to be the 2's place, right? So then this is going to be our answer, which is equal to 2, right? 1's place is 0, so there's no 1's, and then we have 1 in the 2's place, so we have 1, 2, so 2 plus 0 is 2. Does that make sense to everyone? Okay. So we're going to... So when we're adding two one-digit binary numbers, right, we're going to have our results going to have 2 digits, right, because we can go up to values of 1 plus 1, which is going to be equal to 2. Right. So when we're making our calculators, right, we know intuitively that these are the answers, but when we're doing the outputs, right, computers and our logic, it's still either on and off. So we need to analyze this different placeholders as different equations, kind of. So we need to figure out a Boolean expression that would give us the answers in the 1's place as well as the 2's place, which we're going to be calling our sum and our carry for the to be carried to the next place. So how do we find a Boolean expression for these? So basically we're going to try to, so for our case, we're just going to find patterns and common expressions we already know. So for a half adder, that's basically just going to be, when we're adding 2 digits, And then we're getting two outputs, our sum, which is in the same place, and our carry, which is the one that goes to the next place. And so if we separate our carry and our sum and we look at those, we see that they're very similar to expressions we already know, which are our AND and our XOR, right? So 0 plus 0, we're just going to get zeros for both. 0 plus 1, we're just going to have 1 in the sum. 1 plus 0, same thing, but inverted, one of our properties again, sum. And then 1 plus 1 is 2, so 0 in the sum and carry is 1. Okay? And when we compare these end up being the same as these two expressions that we've already had a lot of practice with. So when we're building our calculators, we're actually going to be representing these inputs and outputs as these gates, with these gates. So we're going to be, right, so our AND is going to be representative of our carry, and then our XOR is going to be representative of our sum. Are we good? No. Oh.
One more time. I was looking
Nope.
at carry. Yeah.
Are the shape, they should be in the front of the section. I can write them on the, so.
Yeah, they put them only on page 1.4.
So yeah, we have symbols for all of these different things. So not is going to be this triangle with the dot. And is this one. Or is a little curved. So those are. So then say we're adding a 2-digit number, right? And so now we're going to analyze the second digit, so the 2's place, right? But so what if for our 1's place we already had 1 and 1, we had that carry, right? So this is where the full adder comes in. So this is going to be for all digits past the first digit, right? Because now for the other digits, they'll usually have a carry, either 1 or 0, depending on if the digit before that had excess. So the full adder is a little more complicated. You won't necessarily get the patterns right ahead. We've given it to you. So these are going to be your inputs. So A, B, and C. C in from your last half adder from your 1's place. And then your outputs are C out, which is going to be the 4's place, so our third digit, and then S, which is going to be our sum, which is the second place. So just based on this diagram right here, can anyone figure out what the expression for S and C out would be? And you can kind of work it out on paper if that's easier. And just be careful. So the dots here, so I know there's a lot of overlap here. So dots are explicitly where things are connected. Overlaps like this aren't connected unless they have a dot explicitly placed on it. So you don't get confused around this area. So I guess we can try to go over this together. So, right? So what's this gate right here? XOR. Right. So this is going to be the XOR of A and B. Right? And then that goes into this other XOR gate. Right? So that's going to be XORed with what? What's the other input to that? Cn, yeah. So, and then that's going to give us S. So our expression for this is going to be parentheses A XOR B, and then that XORed to Cn.
Is that only one of the A, B, and C's would be a 1? Does that mean only one A, B, or C can be a 1 or S can be 1?
Yeah, so, right, we can see it here in this table. But, right, so if our first, so yes, but see, in this case, right, so if A and B are both 1, right, if those are, when those XOR, we get a 0. But when we XOR that with Cin, that's going to come out a 1. Right? So if we add 1 plus 1, we're going to get 2, which is, we can carry 1 digit. So say 1 plus 1 is 2, we can carry that out. But if we have 1 plus 1 plus 1, that's going to be a 3. So that carries out to 1, 2, right? So 1 to the next place, and then the 1, 1 that stays there. Kind of like when we add, say, like 9 plus 4, right? We keep 3 there and then carry 1 over still. We don't carry. That makes sense? Yeah. And then for Cout, we have our inputs here, A going here, B going here. What's this gate? And, right. So we're going to do an AND of A and B. And then we're also going to have another AND gate. So that's going to be from A XOR B from the first one we did. That's going to be ANDed with Cin. And then these two AND gates go together into an OR gate. Right? So it's going to be, you're going to have 2 parentheses, basically with the in-between of the plus sign for OR, with each parentheses having those equations. So AB, so A and B, so A multiplied by B, and then parentheses A XOR B multiplied or ANDed by Cin. That makes sense? So I think the expression is it written somewhere in the book?
I think this
Right.
is 147. What you're looking
I can,
for. The Cout is, if you look for A exclusive B times Cin.
so I'll just write it on the board here. Can I erase these, or do people still want the gate symbols? Good. So for our sum, that's going to be equal to A exclusive OR B, that first gate over there. And then that's going to be exclusive ORed to Cin, right? Following the 2 gates up top, which lead to S. And then Cout, a little more complicated. We have 2 main parts that are going to go through an OR expression together. So our first part is just going to be A and B. Our second part is going to take our result from that first gate, so A exclusive OR B. It's going to be ANDed with Cin. Okay. Is everyone kind of clear on how we kind of got that from the diagram to the equation? Okay. And so if we want to kind of confirm that, so last table, I think it's in your book, right under the picture for the full adder. So this is kind of just verifying the equations that we got already for our sum and our Cout. So we can go through, I'll give you a few minutes to kind of go through that and just kind of verify for yourselves what the value is. Okay, so we're going to start talking about the actuality calculator that we're going to be building now, that we know the fundamentals about the half adder and the full adder. So we're going to be making a calculator that can add 2 two-digit numbers together, right? So because it's 2 digits, our output is going to be 3 digits due to that carry from that final digit coming out. And so basically, right, if we have two digits, so 2 places, our maximum number can be 3. And so 3 plus 3 is going to be 6, so our maximum values are going to be 6, and our minimums, of course, are going to be 0. And because we have 2 digits, basically, so remember, our ones place is going to have that half adder that we just talked about. And then our twos place is going to have that full adder to take the carry that came from the half adder. So these are going to get inputs A and B, as well as this. And for our purposes, right, we're going to interpret the digits all separate. So this is going to be our first number, A1, A0. Those are going to be our digits. So the ones place and the twos place. And then we're going to have B1, B0. Those are going to be this ones place and the twos place of the second number. And this is just so, because for the adders, right, we're only going to have the numbers corresponding to their places go into the correct adder. So our half adder is only going to take our ones place. The carry is going to go into the full adder, and then that's going to add these two, and whatever, if there's any excess that came from these two, say if we added 1 plus 1. Is everyone good on how that kind of works? So this is going to be the carry. This is going to be a sum of the zeros placed. Does anyone have any questions about this?
Do you have a particular, before we go to the machine, or is it all about going to the machine? When I say machine, are we going to the computers?
Yeah, we'll be going to the computers in like a minute and build.
Are you trying to get us to experiment to see what it says, or would you like to write a digit up there to see how this all looks before we go here?
We're just going to go right to it.
Okay.
Does anyone have any questions about how the full adder and the half adder are connected? We all kind of understand how that works. Okay. Right, so the blue circuit boards that you've made, they have those inputs already built into the board. So we have switches to represent the ones and the zeros of the numbers we want to input, and then we have LEDs to represent the outputs. So when the LED turns on, that's going to represent our output being a 1 or a 0. So that's how that board works. Our main goal for the calculator is for you guys to build the rest of the circuitry. So that board only really deals with inputs and output values. We have to build the gates, so the nots, the ands, all of that. That's more going to be what you're building. And then connecting back to the board so it can light up the correct answer. So in physical circuitry, these gates are going to be represented on these things called IC chips. They look like kind of little bugs. They have these pins sticking out. And basically, they're components that have many gates inside them. So they usually have about 8 wires sticking out on any side, both sides. Right. They have wires sticking out of these sides, and usually, with the part number, you'll know, usually, there'll be gates inside. So some pins of these gates will be inputs, and then some will be outputs. You won't have to know what gate, what pin is supposed to be what. You'll have diagrams to correspond with the correct chips. If that makes sense with how that works. So the thing about this LED calculator is that, as you guys kind of saw with how the full adder and the half adder are, it's a little complicated. There's a lot of gates that you're going to be using. And so when you're building that on a physical level, it's going to be a little messy, right? Because instead of drawing things, you're going to have wires everywhere. You're going to have parts everywhere. It's not going to be the same. So we're going to start by making that circuit on your SimCir application before we start actually making the physical version of the calculator. So if you guys could pull up the SimCir application right now. Okay, so we're going to get started. So if you guys have your SimCir application open. So what I have on here already is basically what that blue circuit board you guys have has. So it has these 4 switches, 2 on top, 2 on bottom to represent the 2 two-digit numbers, and then our output in LEDs. Right. So as I said, this calculator is going to consist of 1 half adder, which then leads to 1 full adder, and those results are going to be your results. So if you look at page 144 in your book, that's going to have your diagram for your half adder. Right. And so for the half adder, that's going to be for our ones place, so for our A0 and our, sorry, typo, for our B0. So that's going to be our ones place, A0, B0.
Can you give us a time to catch up with you to put these things on our spaces?
Yeah.
What program are you in? 'Cause I don't see you.
Did you guys use the website? So it's going to be this website top.
It wasn't that, it's like,
Scroll down. We scroll down. Because how do we get this A1,
We don't
B1?
use-
Oh, we have to go to a different.
Oh,
You rename the toggle.
if you double click, you can rename what the toggle is called.
Oh, okay.
Yeah, so you can double click on it and it'll say enter device name. And you can just enter what you'd rather have it called. That's easier. I'll just redo these. There's your toggles. And just click.
It should be 0, not 1.
Right, we use 0 for our ones place instead of 1. That's just the notation we use for these.
Is there any other action besides entering the toggle name? Because what I, if the toggle name to rename it, it does nothing.
You need to press enter and it should load the name on. Yeah, and so our zeros are basically our ones place and the A1, B1 are our twos place. So this plus this. Yeah, and then our outputs are going to be LEDs. So S0 is the sum from our half adder, which is our ones place. S1 is the sum from our full adder, which will be our twos place. And C out is the carry from that full adder, which will be our fours place. And then this is how it is on the board as well. So on the board, our inputs are laid out in that way as switches, and then our outputs are going to be LEDs. And then just remember to connect your DC power source to all of those toggle switches. And so once you do have those on, right, so our first place, so the ones place, is going to be our half adder because, right, there's no carry we need to worry about. It's already the first place. So if you look at page 144, that's going to have the gate schematics for your half adder. Okay. Right, so for S is going to be our S0, which will be the ones place of our sum. So that's just going to be A XOR B. So if you guys can drag XOR gate. And right now we're just worrying about all the 0 places. So A0, B0, S0. And then for your carry, you're going to have an AND gate. That's going to be the AND of A0 and B0. Right? But instead of having a CO, right, that's going to be your carry for the next part of your full adder. So then this is going to end up being an input to the next part of our circuit. So if we remember, our full adder uses 3 inputs. So the carry from the last part of the number as well as the inputs of the A and the B. Right. Does anyone else have any questions about this?
That phrase carry, can you clarify that other than that? Like, I think I'm not.
Yeah, so kind of like when you add numbers, like if you're adding 14 plus 9, right? 9 plus 4 is 13, right? But we can't put 13 down here. So we have that carry of a power of 10, so that carries out here. So basically we do the same thing but in powers of 2. So anytime you have more than like that place's value, it'll go to the next place.
You can add 1 and 1 and get 2 because you're not allowed to have a 2 in binary.
Yeah, but a 2, it can be represented as 1, 0, so that carries up to the next place. So if we have, say, so this is like the largest that's going to be on your calculator. If we do 1, 1 plus 1, 1, so that's 3 plus 3, right? So it's 2, 1, 2, and 1, 1, so 2 plus 1 is 3. So 3 plus 3, right? Our first place is 1 plus 1, but of course we can't put a 2 here, so that's going to be a 0 carried by a 1. Right? In our very last place, we have 1 plus 1 plus 1, right? So that's going to be a 3. And so you can take another 2 out. That carries out, but right, it's kind of like when you still add 9 plus 4, you still have something left in that place. So we still have that 1 here, 1, right? And so then that our answer is 1, 1, 0, right? Because then this is the 1's place, so no 1's, 1, 2, 1, 4, 4 plus 2.
2-digit binary numbers, we might get a 3-digit answer.
Yes.
Which is why she has 3 LEDs.
Yeah, so basically the idea is that you could have something carry out from this last digit, and so that's why we need that extra place.
That's why you need 3 LEDs in the right-hand corner.
Yeah.
And she's going to work out how you turn those on for 0 or off for 1. Right?
Does this make more sense to everyone?
Yes.
Okay. So right now, so far on here, we just have the half adder, so just from our calculations from that first 1's place. So now we're going to move on to the full adder, which is, the visualization is on page 146. So now we're just adding that 2's place, so A1, B1, and then any carry that came out from that 1's place, which is that AND gate we already have on there. Right. So we have more XOR gates. So first, let's solve for our S, which is going to be our S1. So now we're done with A0, B0. We've already added that place. So this place is done. Now we're only concerned with the 2's digit place, which is going to be A1, B1, and this AND gate's output, which is the CIN. So those are our 3 inputs. Okay. So if we look at that top of the full adder, we have an XOR gate. And those inputs are A and B, so that's going to be A1 and B1. So A1 XOR B1. So once you have that one XOR gate, if you look at your diagram, we see that that XOR gate then leads to another XOR gate. So we're going to drag another gate on. So if we look at the full adder on page 146, we see that the XOR of A and B leads to another XOR gate, in which the second input is CIN. So that's going to be that carry we just got from that half adder, which is going to be this AND gate right here. That's our CIN. So that's going to go to this XOR gate. Okay. And that is directly going to be our second value for our sum, so the 2's digit. Right, if we add, we haven't gotten to the last digits, right? We do 1 plus 1, we can get 2, 1. Okay. And so once you have that S1 solved, the only thing left we have is that C out, which is going to be our 4's place digit, so the 3rd place. Right. So if we look on our page 146, that diagram, we're going to have 2 AND gates, which lead to 1 OR. 146.
Okay.
Okay. We're going to have two AND gates, which lead to one OR gate. Okay. And that OR gate leads to C out.
What fills up those A gates?
Right. And then you can put the inputs to those AND gates. So our first AND gate is going to just be A1 and B1. It's a little messy just because of the way this is formatted. So A1 and B1. Right.
Those two be first and?
Yes. And then our second AND is going to AND our C in. So that one AND we had from A0, B0, that's going to be the input to the second AND gate. And then the other input is going to be A XOR B, which you already used for the S1. So it's going to be this XOR gate. I will move all of these over. This is a little. This is the correct answer. Like, so if you wire this correctly, this should be what your LED should be doing. So if none of them are on, you should have, if none of the toggle switches are turned on, these lights should all be off.
Right.
If A0 is on, then you should have S0 on. If A0 and B0 are on, then you should have S1 light up.
Oh, okay, I see.
If you do A1, A0 both on, then you get those S1, S0 both on. If you do A1, B1 both on, you'll get C out on and then the other two dim. If you then also light up A0, so A1, A0, B1 all on, you'll get C out and S0 on.
Right.
Then you light them all up, you should get S out and S1 in. So just confirm that that's what you get.